Every volcano on Earth is supposed to form in one of three ways. Scientists have known this for decades. It's basic textbook geology. And for just as many decades, one of the most famous, most active, most closely studied volcanoes on the entire planet has stubbornly refused to fit into any of them. Mount Etna sits directly above a subduction zone, exactly the kind of location that should produce one specific, well-understood type of volcanic activity. Instead, it erupts lava with a chemical signature that belongs somewhere else entirely, the kind of lava you'd expect from a hotspot volcano like Hawaii, except there's no hotspot anywhere near Sicily. For years, nobody could explain that contradiction. This year, a team of researchers finally may have, and the answer turns out to be even stranger than the mystery itself. Today, we're breaking down exactly what they found, why Etna has been such a genuine enigma for so long, and why scientists are now saying this volcano might be the only one of its kind on the entire planet. No guessing, no dramatizing, just the facts, the science, and what it actually means. Before we get into it, here's a question for you. Do you think every mystery in a field as old and well studied as geology has already been solved? Or does something like this surprise you? Let me know what you think in the comments. If you want to be the first to know every time research like this comes out, subscribing genuinely helps this channel keep going, and it's completely free. All right, let's get into exactly what makes Etna so strange. To understand why Etna has confused geologists for so long, you first need to understand the three ways volcanoes are normally supposed to form, because Etna checks the box for one of them geographically, while completely failing to check it chemically. The first category is constructive plate boundary volcanoes, forming where two tectonic plates are actively pulling apart from each other, leaving space for mantle material to rise up and melt as the pressure on it releases, the kind of volcanism you find along the mid-Atlantic ridge. The second category is destructive plate boundary volcanoes, forming at subduction zones, where one plate is forced underneath another, carrying water down with it into the mantle. That water lowers the melting point of the surrounding rock, generating magma and frequently explosive volcanoes, Mount Fuji in Japan being the textbook example. The third category is hotspot volcanoes, forming in the middle of tectonic plates entirely, far from any plate boundary at all, where unusually hot material rises from deep within the mantle in a fixed plume, producing volcanic island chains like Hawaii as the plate slowly drifts overhead. Mount Etna sits geographically right where Category 2 should apply, positioned near the boundary where the African plate is being forced underneath the Eurasian plate. But its lava doesn't behave like typical subduction zone lava at all. Etna produces alkaline lava, a chemical signature that geologists strongly associate with hotspot volcanism, the kind of chemistry you'd expect to find in Hawaii, not Sicily. There's no hotspot beneath this part of the Mediterranean, though. No fixed plume of unusually hot mantle material that would normally explain that specific chemistry. So for decades, Etna has presented geologists with a genuine contradiction, a volcano positioned exactly where subduction should be driving its formation, chemically behaving like something that shouldn't exist in this location at all. This isn't some minor academic curiosity either, buried in an obscure corner of volcanology that nobody outside the field cares about. Mount Etna is the most active volcano in Europe, rising over 3,000 meters, nearly 10,000 feet, above sea level on Sicily's eastern coast, erupting multiple times every single year. According to the Smithsonian Institution's Global Volcanism Program, it has one of the longest documented eruption records of any volcano on the planet, with observations dating back to roughly 1500 BCE. This is a volcano that has been actively monitored, sampled, and studied by modern geologists for well over a century, using virtually every instrument and technique available to the field. And despite all of that sustained attention, its fundamental origin remained only partially understood, a genuine gap in one of the best studied volcanic systems on Earth. Several explanations had been proposed over the years, and each one solved part of the puzzle while leaving another part completely unaddressed. Some researchers suggested Etna's magma came from an unusually old, stable pocket of material sitting in the upper mantle, disconnected from the current subduction geometry entirely. Others argued Etna simply represented a genuine fourth category of volcano, one that would require geologists to write an entirely new classification just to describe it. Each hypothesis had some genuine supporting evidence, and each one had real problems that kept it from fully explaining both halves of the contradiction at once, Etna's subduction zone location, and its distinctly hotspot-like chemistry. Then, this year, a team led by Sébastien Pillet at the University of Lausanne, working alongside researchers from the Istituto Nazionale di Geofisica e Volcanologia in Catania, published a study in the Journal of Geophysical Research, Solid Earth, that may have finally resolved it. Their research drew on rock samples spanning roughly 500,000 years of Etna's eruptive history, giving them an unusually long timeline to work with when reconstructing exactly where this volcano's magma has been coming from. What they found was that Etna isn't forming fresh magma shortly before each eruption, the way most conventional volcanoes do. Instead, Etna appears to be tapping into small, pre-existing pockets of magma that have been sitting quietly in the upper mantle for a very long time, roughly 80 kilometers, about 50 miles beneath the surface. As the African plate continues its slow collision with the Eurasian plate, the bending crust near that subduction zone develops fractures, and that ancient, already existing magma gets squeezed upward through those cracks, essentially the same way you'd wring liquid out of a soaked sponge by bending and twisting it. That deep, pre-existing pocket of magma is what explains the hotspot like alkaline chemistry. This material formed and sat in place long before the current subduction activity began actively squeezing it toward the surface, so it never picked up the chemical signature you'd expect from freshly generated subduction zone magma in the first place. Based on this mechanism, the research team proposes that Etna may actually belong to a genuine fourth category of volcano, one that's barely been studied at all until fairly recently, known as a petit spot volcano. This category was first identified by Japanese geologists back in 2006, and up until now, every known example has been a comparatively small submarine volcanic structure, tiny bumps on the ocean floor fed by exactly this kind of pre-existing upper mantle magma pocket, being squeezed out through cracks in a bending tectonic plate. Mount Etna, if this classification holds up, would be something genuinely unprecedented, an enormous, continuously active stratovolcano, one of the largest and most famous in the world, apparently being fed by the exact same mechanism previously only ever observed powering small, obscure volcanic bumps on the ocean floor. Lead researcher Sébastien Pillet has been direct about what makes this finding so significant, drawing a striking contrast between the small scale of every previously known petit spot volcano and Etna's genuinely massive scale. If Etna really does belong to this category, it suggests these previously overlooked deep magma reservoirs are capable of producing far more dramatic, far larger scale volcanism than anyone in the field had previously assumed possible. That's a meaningful shift in how geologists think about where large volcanoes can come from. It's not just about being positioned at the right kind of plate boundary or sitting above a hotspot plume. There may be an entirely separate pathway involving these ancient, dormant magma pockets that geologists have mostly overlooked until very recently, precisely because the known examples were always so small and unremarkable. It's worth understanding what this deep material actually is a little more precisely, because the term upper mantle can sound vague without context. Geologists refer to the specific layer where this magma has apparently been sitting as the low-velocity zone, a region within the upper mantle where seismic waves travel measurably slower than in the rock immediately above and below it, a signature that typically indicates the presence of partially molten material. This zone exists at roughly this same depth beneath large portions of the planet, which raises a genuinely interesting follow-up question. If Etna is tapping into material from this zone, are there other places on Earth where similar ancient magma pockets exist, simply waiting for the right combination of tectonic bending and fracturing to eventually squeeze them toward the surface as well? There's also something worth appreciating about how this magma behaves once it does reach the surface, because it helps explain Etna's famously frequent activity. The researchers describe Etna as functioning something like a leaking pipe, rather than a system that builds toward isolated, discrete eruptive events the way many conventional volcanoes do. Because that deep magma source is being continuously squeezed upward through an established network of fractures, rather than requiring an entirely fresh batch of magma to form before each individual eruption. Etna maintains what the researchers describe as an essentially open, pipe-like conduit to the surface. That structure keeps the volcano almost constantly degassing and frequently producing the kind of relatively small, frequent lava fountaining events Etna has become famous for, rather than building toward the rarer, much larger explosive eruptions associated with volcanoes that need to accumulate an enormous fresh magma chamber before they can erupt at all. This also helps explain something that had puzzled researchers for years about Etna's specific eruptive behavior. Most active volcanoes show a fairly clear relationship between how long they've been dormant and how large their next eruption tends to be, since a longer quiet period generally means a larger volume of fresh magma has had time to accumulate underground. Etna doesn't cleanly follow that pattern, frequently producing dramatic eruptions on remarkably short notice. A continuously leaking pre-existing magma source, rather than a system dependent on slowly accumulating a fresh reservoir before every eruption, offers a genuinely coherent explanation for that irregular, frequent behavior. It's worth understanding how researchers can even tell the difference between these different types of magma in the first place, since this entire mystery ultimately comes down to chemistry, not just location. Geologists analyze the specific trace elements and isotope ratios locked inside volcanic rock samples, essentially a chemical fingerprint left behind by whatever process originally generated that magma deep underground. Subduction zone magma typically carries a distinct signature related to the water and sediment being dragged down with the subducting plate, while hotspot magma carries a different signature tied to the deep, primitive mantle material it originates from. When the research team analyzed samples spanning Etna's 500,000-year eruptive history, they found a chemistry that kept pointing toward that hotspot-like signature, generation after generation, eruption after eruption, without the specific markers you'd expect if fresh subduction zone processes were actively generating that magma just before each eruption. That consistency over such an enormous span of time is part of what led the team toward the idea of a static, ancient, pre-existing magma pocket, rather than magma being freshly generated by ongoing subduction, since fresh subduction-generated magma should have shown at least some of those expected subduction signatures somewhere across 500,000 years of samples. The petit spot category itself deserves a bit more context too, since it's genuinely obscure even within specialized geology circles. When Japanese researchers first identified petit spot volcanism back in 2006, they were studying small, previously unexplained volcanic bumps scattered across the deep ocean floor, particularly in the Northwest Pacific, features far too small and far too disconnected from any plate boundary or known hotspot to fit into either of the two established categories geologists already understood well. Further research determined these small submarine features were being fed by exactly the mechanism we've been describing: pre-existing pockets of magma in the upper mantle, squeezed toward the surface as the oceanic plate flexed and cracked while bending downward at a subduction zone, entirely independent of any active melting happening at that moment. For nearly 2 decades, every confirmed petit spot example remained small, obscure, and almost entirely confined to a fairly narrow academic conversation among specialists studying seafloor volcanism. Nothing like a globally famous, actively monitored giant like Etna. That's precisely why this new proposed connection is generating so much genuine interest within the field. It would represent by far the largest, most consequential example of this specific volcanic mechanism ever identified anywhere on the planet. This finding also carries real practical implications for how scientists monitor and think about Etna's future activity, beyond simply satisfying decades of academic curiosity. If Etna truly is being fed by a continuously leaking, pre-existing deep magma source rather than a conventional subduction-driven system that changes what specific signals researchers should be watching for when trying to anticipate the volcano's future behavior. Monitoring networks built around the assumption of a fresh, actively forming magma chamber look for a fairly specific set of precursor signals. A system instead built around continuous leakage from an ancient deep reservoir may show a genuinely different pattern of subtle warning signs before larger eruptive episodes. Information that could meaningfully refine how volcanologists interpret Etna's frequent seismic and deformation data going forward. It's also worth grounding this in Etna's actual recent behavior. Since this isn't a purely historical or theoretical volcano sitting dormant somewhere, it's actively erupting right now, in the present tense. Most recently, eruptive activity was observed from late December 2025 through the first few days of January 2026, producing ash emissions and lava flows near the Valle del Bove, a large valley cutting into the volcano's eastern flank formed by previous collapse events over Etna's long history. That's just one recent episode in a genuinely continuous pattern. This is a volcano that produces multiple eruptive events almost every single year, which is exactly the kind of frequent, relatively short notice activity. This new leaking pipe model is specifically trying to explain. Every time Etna produces another eruption like this one, it becomes another data point researchers can eventually use to test whether this petit spot hypothesis actually holds up against real ongoing volcanic behavior, rather than just historical rock samples. There's a broader implication worth sitting with here too, one that extends well beyond this one volcano in Sicily. Etna isn't the only well-studied volcanic system where geologists have struggled to fully reconcile a volcano's tectonic setting with its chemical behavior. Similar puzzling mismatches between location and lava chemistry have been noted at a handful of other volcanic systems around the world over the years, cases where researchers have proposed everything from unusual mantle plumes to contaminated crustal material to explain an unexpected chemical signature. If the petit spot mechanism identified here genuinely does explain Etna, it hands researchers studying those other unusual cases a new, testable framework to check their own data against, a specific, well-defined mechanism involving ancient trapped magma and tectonic flexing, rather than continuing to treat each unusual volcano as its own isolated, unexplained curiosity. Science tends to advance exactly this way. A single well-resolved mystery in one heavily studied location often ends up providing the missing piece needed to finally make sense of several other stubborn puzzles that researchers had been circling separately for years, sometimes without even realizing how closely related their individual mysteries actually were. It's also worth being fair about exactly how settled this conclusion actually is, since that's an important part of reporting on science accurately rather than treating every new study as instant, unquestionable fact. The researchers themselves have been careful to frame this petit spot classification as a compelling new hypothesis backed by genuinely strong supporting evidence, not as a completely closed case that the rest of the geology community has already universally accepted. Reclassifying a volcano this famous, this thoroughly studied, into a genuinely new category typically takes years of additional scrutiny, independent replication by other research teams, and continued testing against new eruption data as it comes in. That's not a weakness in this specific study. That's simply how rigorous science is supposed to work. A single well-designed study built on 500,000 years of rock samples can shift the leading explanation dramatically, without that immediately becoming the final, permanent word on the subject. Given how long Etna has resisted a full explanation already, it wouldn't be surprising if this new model faces genuine challenges and refinements over the coming years. Even if its core insight that ancient pre-existing magma pockets can apparently fuel volcanism at a scale nobody previously thought possible, ultimately holds up. So where does this actually leave us? A volcano that has been intensely studied for well over a century with one of the longest documented eruption records on the planet may have just had one of its most basic mysteries, quite literally how it works at all, resolved by researchers looking in a place nobody had seriously considered before. A small, previously obscure category of submarine volcanism that had never once been associated with anything on Etna's scale. If this classification holds up under further scrutiny and the researchers themselves are careful to frame it as a strong new hypothesis rather than a completely settled conclusion, it suggests that even our most extensively studied volcanic systems can still be hiding a fundamentally new answer, sitting in plain sight roughly 80 kilometers beneath our feet. We'll keep an eye on how this research develops as other teams examine and test this petit spot classification against Etna's ongoing activity. If this kind of deep dive into genuinely well-established, peer-reviewed science is something you'd like to see more of, subscribing helps this channel keep making it. And if you found this one worth your time, leaving a like genuinely helps more people find it too. Thank you so much for watching. Stay curious, stay informed, and I'll see you in the next one.